In this video, we will begin our discussion of addition reactions to alkenes. So as we saw in the previous chapter, we can generate alkenes pretty easily using elimination reactions. But once we have our alkane or alkene functionalized, it's often very useful to take it further on in its functionality. And one of the ways we can really functionalize alkenes is with addition reactions. So the general reaction scheme for an addition reaction to an alkene, I'm just going to draw a generic alkene, and then we're going to add AB. And in an addition reaction to an alkene, what we're left with is the alkane, in most cases, where AB has added across the double bond. So as we see here, we have a pi bond. So pi bonds are definitely high in electron density. And because they're high in electron density, this makes them nucleophilic. So a CC double bond is primed to attack an electrophile. And as we see, if we write AB as a polarized molecule, delta positive, delta minus, we can have a double bond attack AB as the electrophile and push out B minus. One of the most common ways we can functionalize an alkene is with the addition of HX. So a mineral acid, so something like HCl or HBr, where we have the delta positive on H and the delta minus on X. So if we write a series HF, HCl, HBr, HI, what we see is that that reactivity is going to trend with acidity. So where HI is the most acidic and HF is the least acidic. In terms of reactivity, we'll see that HF is much less acidic, much less reactive than HCl, which is less reactive than HBr, which is much less reactive than HI in these addition reactions. So what does the general mechanistic principle look like for this reaction? So we start with our alkene, and we're going to have HX floating nearby. Remember, the H, the proton on this, has a delta positive charge, it has a partial positive, so that's our electrophile, and our nucleophile is our X. So since our double bond, our alkene, is nucleophilic, we're going to have nucleophilic attack on the H. We're going to push out X minus, so we'll lose X minus. And then what we'll be left with is we've now gotten rid of the double bond, the pi bond has disappeared. We've added H to one of the carbons, and we've generated a carbocation intermediate. This carbocation intermediate, like we saw in the past, this is going to be sp2 hybridized, and it's planar. So that means that we can have attack from either side, either face of the trigonal planar carbocation. And then in the final step, we're going to have X minus, we're going to have attack on the carbocation, having a net result of adding HX across the double bond. So the alkene has been reduced to a single bond, and we have addition of HX across. So you can imagine that we could also have ended up with a functionalized alkene where the H and the X are reversed. And since we haven't specified the functionality on this CC single bond or the CC double bond, either of these are equally likely. But what happens if it's asymmetric? And it turns out if it's asymmetric, then there is a preference for which side the H goes to and which side the X goes to. So let's examine another example where we have an asymmetric alkene. So let's look at this example here. So we're going to add HBr to this alkene. So we can imagine there's two possible options. We can add the H to the secondary position and the Br to the primary position, or we can add the Br to the secondary position and the H to the primary position. And in order to examine which one of these is the major product and which one of these would actually not be formed in this case, we have to examine the mechanism a little bit. So as we saw, we're going to have protonation of the alkene by HBr. And that's going to add H to one of the positions and form a carbocation on the other position. So there's two possible options here. We can add the H to the secondary position and have a primary carbocation, or we can have the H added to the terminal position and have a secondary carbocation. As we saw in previous videos, having a primary versus a secondary carbocation, the secondary carbocation is going to be much, much more stable than the primary carbocation. So what we see is that this primary carbocation actually doesn't form. Primary carbocations are very unstable, as we've seen in previous videos. So the secondary carbocation is what's going to form. And then that Br minus is going to come in and attack the carbocation, thereby neutralizing it. And we end up with the ultimate result of the Br being substituted at the secondary position. So this substitution pattern is called Markovnikov's rule. And what Markovnikov's rule states is that the substitution occurs at the more substituted position, at the more substituted position. So in this case, we had the option of substituting at the primary position or the secondary position. And since this is a Markovnikov's rule governed reaction, the Br will substitute at the more substituted position. An alternative way to say this is that the H will go to the location that has more H's. So in our starting material, we have 2 H's at the terminal position. We have 1 H at the internal position of the alkene, so our H would go to the terminal position, and our Br would go to the more substituted position. Just to look at another example of Markovnikov's rule, say we had an alkene like this, and we added HCl. Again, there's 2 possible options that form from 2 possible carbocations, so we can imagine one intermediate where we have a carbocation on the tertiary position, and another intermediate where we have the carbocation on the secondary position. So we have secondary versus tertiary. And we see that because a tertiary carbocation is more stable than a secondary carbocation, we will favor the formation of the bromo substitution at the tertiary position. So we'll have bromide attack at the tertiary position. And we'll end up with the tertiary alkyl bromide. So the substitution, we would call this a Markovnikov substitution because the substitution occurred at the more substituted portion of the alkene. The one thing that we want to be aware of is because we are invoking a carbocation intermediate, we run the risk of carbocation rearrangement. So as we saw with SN1 and E1 reactions, if we generate a carbocation intermediate, we do run the risk of rearrangement. So let's look at another example. So say we have this alkene here, and we're going to add HCl, and we're asked what the product is. Now, looking at this, we have an HX addition to an alkene. This is going to be a Markovnikov addition, so we expect the Cl to be at the more substituted secondary position versus the less substituted primary position. So if we weren't being careful, we would expect a substitution that looks like this. However, this is not the ultimate product, and if we examine the mechanism, we'll see why. So if we examine the mechanism, we're going to have protonation of the alkene by HCl. So we're going to grab that proton, push out Cl minus. That carbocation will form where it's more stable. We've added an H here. And if we were to just have Cl rebound and attack this carbocation, this is where we would get our secondary alkyl chloride. However, if we notice, we have a hydride right here. And as we've mentioned previously, if a hydride or a methyl shift or a hydride or an alkyl shift can occur to stabilize the carbocation intermediate, it will occur. So in this case, if we take this hydride and shift it over one, so this is our hydride shift. If we move that over, we'll see that we moved the hydride here, and we've instituted a tertiary carbocation. So we went from a secondary to a tertiary carbocation, which is more stable. So this is a favorable carbocation rearrangement. And then in the final step, we would have rebound by the chloride ion to attack that carbocation, and thus result in not the secondary alkyl chloride, but the tertiary alkyl chloride. A similar example with a different kind of shift, we could have this kind of a similar structure, and we add HBr. And I'll skip writing the mechanism, but you can imagine that alkene is protonated by HBr, so we end up with a secondary carbocation. But We have a methyl that can shift next to it, so we're going to take the methyl and we're going to push it over. So this is our methyl shift. And what we're left with is a tertiary carbocation. Again, we've gone from a secondary to a tertiary, so it's favorable. And we have rebound of the bromide ion to get, instead of the secondary Markovnikov directed product, we'll get the Markovnikov directed product with also a methyl shift that's occurred. So we end up with, instead of a secondary, a tertiary alkyl bromide.